Marwan Omar, and today, or tonight rather, I'm going to do a presentation on the lower bound theory, which is one of the required presentations for our COT 5405 class at UCF. Let's get started. The lower bound theory, this is an important concept in our class for design and analysis of algorithms. So the lower bound is an estimate on a minimum amount of work needed to solve a given problem. So this is what this technique, this is how this technique is defined as. The estimate on a minimum amount of work needed to solve a given problem. I can easily relate to this, I think, because I'm working on some research problems currently as part of my research work. And I have some experience from research papers with lower bounds. So, for instance, we need a minimum amount of work to make our NLP systems, for example, the natural language processing systems, solve the problem with the adversarial attacks. We are trying to make our systems or our NLP models robust to adversarial attacks. So we are estimating, we are counting or computing rather the lower bounds to see how much work we need to defend our NLP models against adversarial attacks. Here are other examples. The number of comparisons needed to find the largest element in a set of n numbers. So how many comparisons do we need to do to, for example, find a given number, maybe a missing integer in an array, or the number of comparisons need to sort an array of size n. So if we have an array of size n, let's say 100 elements within an array, or 1,000 elements, if this is something within the industry, then we will need to do comparisons. So to find out how many comparisons we need, we can utilize the lower bound theory or proof. Also, the number of comparisons necessary for searching in a sorted array. If the array is sorted either ascendingly or descendingly, how many comparisons do we need to do? Because otherwise, it will be very costly. And when we design algorithms, we need to be mindful of the time, of the cost of the algorithm. That's always an important factor when designing algorithms. Also, the number of multiplications needed to multiply 2n by n matrices within an array, for instance. So the lower bound can be an exact count. So it could be an exact point, or it could be an efficiency class. The tight lower bound, there exists an algorithm with the same efficiency as the lower bound. So again, relating to my own research, when we utilize this technique, the lower bound technique, we try to make our bounds as tight as possible. I've seen some researchers discussing and proposing lower bounds, but we don't know how tight their lower bounds are. So the tighter the lower bound is, the better the algorithm can defend against adversarial attacks. So for the problem of sorting elements within an array, for instance, the lower bound tightness is n log n, which is good. Also, for the uniqueness of an element, we can provide the lower bound tightness, which is required as well. Then we have methods for establishing lower bounds: trivial lower bounds, information theoretic arguments, decision trees, adversary arguments, problem reduction. So let's talk about each one of these. Trivial lower bounds, based on counting the number of items that must be processed in input and generated as output. Examples: finding max element. So a simple example, if we have an array of 100 elements and our goal is to find the max element, so which element has the maximum value within that array, we can use the trivial lower bounds. We can use it for sorting also. If we're trying to sort an array of hundreds or thousands of elements, we can utilize this trivial lower bound. And so it's not always useful, but this trivial lower bound is useful in sorting and uniqueness, as you mentioned. We have next the information theoretic arguments, or the decision trees are important concept. Again, decision trees are important for data structures and algorithms. So a decision tree is a convenient model of algorithms involving comparisons in which internal nodes represent comparisons and the leaves represent outcomes. So we can think of this as a decision tree. So let's say if we have ABC, is A greater than B? If it's yes, then the outcome would be the leave. Then we'll go down to another decision. Then if B is less than C or greater than C, then if it's yes, then we go and take another decision, and so on. Decision trees and sorting algorithms. Any comparison-based sorting algorithm can be represented by a decision tree. We have the number of leaves, which is the number of outcomes. It's greater than or equal to n, and then the height of the binary tree, which is n, and then the minimum number of comparisons. If these computations hold true, then we can say the lower bound is tight. Again, tightness of the lower bound is an important aspect of the lower bound theory or proof, because based on how tight it is, we can guarantee to a certain degree, we can certifiably we can say certifiably that our NLP systems, for example, are robust to adversarial attacks. Now we can talk about the adversary arguments. The adversary argument is a method of proving a lower bound by playing a role of adversary that makes algorithm work the hardest by adjusting inputs. Example 1, guessing a number between 1 and n with yes or with a yes and no question. So let's say we have a guessing example to guess a number between 1 and 10. So the number that we're looking for, which is n, and we have only 10 numbers. Is it number 2? Is it number 3? Is it number 8? So every time we do yes or no. For the adversary, or from the adversary perspective, they put the number in a larger of the two subsets generated by the last question. So we divide into two subsets, and if the number is greater than the first subset, then we traverse the array and look in the other subset. Also, merging two sorted lists of size n. Lists also are an important concept in data structures. So I can also, again, relate to this, because when researchers utilize the upper bound, the lower bound with the adversary argument, again, they are trying to make sure that our NLP systems or machine learning systems are robust as possible against adversarial attacks utilizing this technique. Lower bounds by problem reduction. So if problem P is at least as hard as problem Q, then a lower bound for Q is also a lower bound for P. Another example, if P is finding MST for endpoints in Cartesian plane, then Q is element uniqueness problem, also known as theta n log n. So this was pretty much the gist of my presentation. I know it wasn't too long, but when I present, I try to be concise and to the point, and make sure that I inject my real life experience as much as possible. I hope this made sense to the viewer and to the professor. And if you have any questions about the preparedness of this presentation or this topic, you're welcome to ask questions. Thank you so much for the opportunity to let me present this presentation to you as part of the coursework. Thank you. Bye.